Hi. So first off, I'm Phil Bassignani. For those who didn't catch the intro, I serve as the PFAS technical director at Pace Analytical, and I was responsible for the method development of Pace's ultra short chain PFAS method. Before we get into that, I would like to just kind of give a quick overview of Pace. Pace is we're the largest network of American-owned laboratories. We have over 120 locations. On the map, you will see the blue dots. Those correlate with our 7 PFAS testing laboratories. And the one in particular here that we're focusing on in New England and Mansfield, Massachusetts, is where this work was conducted. A little overview on Mansfield as it sits in the PFAS network for PACE. It is the largest of the network labs. We have 16 dedicated PFAS LC-MSs, out of which 11 SCIEX 5500s is obviously the 7500s, which we'll be doing covering here, and some older 4500s that we use for drinking water work. The prep area is segregated into 3 separate extraction areas, all handling different matrices and different types of samples to eliminate the risk of cross-contamination or other problems. We are a full-service PFAS testing lab. We do EPA 537, 533. Like a lot of the labs, we have our older legacy 537 isotope dilution method that was really modeled around DoD work, 1633. And then under the kind of umbrella of 1633, we do a lot of odd specialty PFAS testing as well, including wipes, passive samplers. We deal a lot with petroleum matrices, top assays, and we additionally do PFAS in food and consumer products with a modified analytical approach on this for 1633. So in the case of food samples, we would take that FDA method front end for extraction and then pair it with the 1633 analysis. And we do have the ability to cryo mill and process samples, particularly the consumer products where they might be dealing with a lot of solid materials that are tough to mill down into fine material to get an efficient extraction. Delay here. Hold on 1 second. I have a delay in my slides not advancing. There we go. You're gonna have to go back one. Here is just some images of the prep lab in the analytical areas here in Mansfield. We have some hoods, both ductless and ducted, and a number of the instruments around the lab. Mansfield is, outside of the PFAS testing, a full-service specialty lab. We have air testing, sediment tissue forensics, petroleum hydrocarbon forensics, and the metals analysis, and a number of the other common areas that you would expect in a full-service laboratory. And now, without any delays, we'll jump into PACE's ultra-short chain PFAS method development. So in the beginning, one of the first things we asked is how we wanted to approach this. And that first approach was, did we want to do a direct aqueous injection method, or did we want to try to pair it with an extractable and an SPE cartridge? To give it some background, PACE first began looking at this back in the Mansfield facility in 2022 as kind of an add-on for the SPE-based extractions, especially the 1633 rolled out. The TFA presence in background consumables, SPE cartridges, bottles, pipette tips, and other things that Holly alluded to earlier, really shelved that development. It was overwhelming the amount of TFA we were finding in consumables that we just kind of put a pin in that and focused on other stuff until earlier this past year. But that work led us to the decision that if and when we were to advance in a method for TFA, it would most likely be a direct aqueous injection method to reduce all of those contributing sources of TFA. Why is 7500? As I mentioned, Pace Mansfield has 11 5500 pluses doing a number of different tests for PFAS, but we really wanted to focus on delivering the best RLs and best quality TFA data we could with the minimal amount of sample interaction and handling. So that ability to get the highest sensitivity for TFA with the least amount of interaction from the lab chemists was critical in the study. And then, one of the things about not just the physical reagents, but the actual chemical reagents in the lab, things are certified. Vendors will tell you use your LCMS grade solvents. But what we found was, even in the case of solvents, the LCMS grade solvents in a lot of cases had higher levels of TFA in them than the UPLC grades or other lesser reagents. So we couldn't really rely on what grade we were buying. Every product has to be tested. Every tip, a lot of pipette tips, centrifuge tubes, all of it. Everything requires detailed testing before use. And once we got through that stuff, we began building our LC method. We evaluated over 12 different LC columns and delay columns, and in different configurations, trying to find that optimal TFA performance. We started with higher injection volumes in the 50 mic range, scaled it down to 5. In the end, we settled on a 20 mic injection that really got the best of the right amount of matrix in sample to get a good peak, but without overloading the chromatography. One of the areas we found is, when we were doing the method validation, TFA would look beautiful. And then the second we started running real samples with some matrix, the chromatography of TFA would fall apart. So there was a lot of work that went into the optimal retention time of TFA and the optimal amount of samples to decide that. For a relatively small number of target compounds, it's a little bit longer of an analytical run, 14 minutes long, but it's got an extended equilibrium time at the end of the run. And this was really critical to keep any shifting or chromatography deviations with TFA. We found that if we really rushed that, TFA's performance would be highly variable. The mobile phase of selections were pretty basic, a straight aqueous mobile phase with a little acetic acid, and then acetonitrile, ammonium acetate, organic phase, very similar to a lot of the PFAS methods out there. At the end of the day, we settled on a Phenomenex delay column, specifically made for short chain PFAS, and Phenomenex polar pesticides LC column, both provided for this testing. The 2.1 column, it made sure that we got it ahead of TFA, ahead of the delay. As if we were to try to extend this to a longer run with additional compounds, this would not be the ideal column. This whole method was really based around TFA performance. And then just some of the aspects of the initial method development. So when we started this, the standard industry and standard providers were still coming out with a lot of these compounds. We knew they were coming, but we didn't have them available at the beginning. So we built our acquisition method knowing that certain internal standards would be labeled analogs would be available at a later date to be immediately implemented in them. And in particular, the C1 sulfonic acid and C2 sulfonic acids at the time weren't available, but we knew they were coming. So, we did the initial validation, and one by one as they came, we inserted them and then had to revalidate the method. But being a direct aqueous injection method, reperforming MDL studies and MRL studies can be done relatively easy. We did extend the analytical run beyond the ultra short chains to have a little bit of overlap with 533 and 1633 in the case of PFBA and PFBS. A lot of times these aren't desired to go with these compounds, but during the method development stage, we felt it was important to have something that carried over into the other methods. That way we could verify when we were pulling archived samples and spikes that things we had known performance for those compounds, we had something in the short chain method to give it some consistency so we knew how we were performing. And then this method we validated for all manners of aqueous samples, from drinking water, groundwater, surface water, even landfill leachates, which is, for TFA, a particularly interesting topic. Not having a published EPA method to base this also off of, we established our own LCMRL study. So we took a low-level spiking replicate at 7 replicates and kept performing it 7 replicates at lower and lower concentrations until we reached the limit for each compound of what that lowest concentration would be. And this is just some statistical data I'm showing here with PFMES, the C1 sulfonic acid. The software used for this can be found on the EPA's website. It's really a useful tool when dealing with unknown compounds and establishing what those thresholds are before you get into your real method development with MDLs. And you can see here, this is our target analyte list, what those theoretical lowest concentrations that we could spike and still achieve a 50 to 150% recovery, and then just what those statistics and how they generated, as well as detection limits and other such numbers. At the end of the day, our actual MDL studies reflected those lowest confidence minimum reporting level numbers very well, and then our actual numbers based on our LOQs. Here we chose 2 nanograms per liter for most compounds to give it that consistency with the drinking water methods, especially for like PFBA and PFBS, where we have methods covered for those, with a slight elevation for PFPRA and TFA based on response and prevalence in the environment. As we got into matrix validations, we pulled old archived samples that we retained, that we had known data on, and then analyzed those same samples by the ultra short chain method that we were putting together, and so to see how they matched up. And what you can see is for most of the compounds, we don't have any data. All we had was PFBA and PFBS. So when we were looking at samples, and the PFBA in a lot of these was at the low end of the threshold, the 7,500 being more sensitive, we had a little more wiggle room on where that fell in the curve. You can see the PFBA, PFBS numbers were fairly consistent, but what we saw as well using a direct aqueous injection method is things like PFBA, the internal standard responses were a lot more consistent. We didn't get the variability from extractions and co-extractive interferences. And for anyone in the laboratory who's experienced with running these types of samples, these landfill leachates, these are really harsh sample matrices. There's a lot of organic content. They're very viscous, a lot of particulates and color to them. Not easy samples to deal with. As we expanded that into drinking water and 1633 samples, we started getting some really interesting TFA data. And a big part of that was samples that would otherwise fall as non-detect for 537 or 533, or have very minimal detections in the short range like PFBA. We saw considerable amounts of PFPRA and particularly TFA in those samples. And you can see in the first example where a sample had no detections of any kind for 537, we're up over 1,000 nanograms per liter for TFA. And that was a pretty consistent trend. Some finished drinking water sources that we were getting right from treatment centers were TFA free, but not always. It's more the exception than the norm that we got samples of TFA below the reporting limit. And again, internal standard responses as compared in most cases were superior to extracted methods. Getting out of the drinking water realm, not really surprising here with 1633 data. Again, the comparability is good, but elevated levels of TFA in samples that ultimately had low-level PFAS detections for traditional compounds. As we get into the calibration scope of things, as I said, this method really focused on TFA, and that was our primary goal in chromatography and needs, especially where we didn't have another method that we could insert TFA into, where most of the other compounds can be inserted somewhere else if we desired. So our actual calculated LOQ and calibration level comes to 10 nanograms per liter. As a typical reported sample, we elevate that slightly to 20, mainly because of the presence of TFA in samples and the expected higher amounts, just to give us a little bit higher range in the calibration. This is an example of a typical TFA calibration. You can see there's not much problems with signal to noise. With a 20 mic injection, we are getting very high area counts. Even at the low end, we're up over 300,000 area counts. And this curve spans from 5 nanograms per liter up to 2,000. On the right, we have an example of the chromatography of the quantitation ion for TFA. versus an instrument blank. So there's really no, as far as the instrument goes, no TFA interference with the delay column in our runs. The other thing I'll point out is that for every compound on the list, we are monitoring 2 transitions, even PFBA and PFPRA. With TFA, there really was no second transition to monitor. So what we treated as the second transition that we monitor is just a sim scan of the primary Q1 ion. We just extend that right through. So we still have a secondary ion, but it's an MSMS or in sim as the qualifier. Our sample prep. So we settled on a 10 mil sample. Typically, a lot of the direct aqueous injection methods collect 5 mils. We went a little higher just to try to get a better representative sample from larger systems. These vials are pre-weighed. They come into the lab. We add the internal standard, a little bit of acetic acid. If this was a drinking water chlorinated source, some ascorbic acid. Samples are lightly mixed in vortex just to allow equilibrium. They're syringe filtered, and then that extract is shot right on the mass spec. So no solvent additions, minimal reagents added to it. Your cleanup is a syringe filter, and we shoot the sample. And then the original tube will determine the weight of what we dealt with to get the volume. QC, we modeled QC after 1633, so we'll do a blank, a low-level LCS, and a mid-level LCS with every sample, kind of following that same scale. If we do need to further any of that with MS, MSDs, duplicates for certain projects, we'll provide additional vols. And then, the reporting limits, as I mentioned earlier, they staggered around what we're historically reporting as well as what we expect to see in samples, not necessarily instrument sensitivity. If we really wanted to, we could see much lower on the 7500, but from a market standpoint, at this time, we don't have a need. And this is, so once we went live and we started running some of the higher level samples, this is an example of some really high concentration TFA samples. You can see this is up over, a billion parts per trillion. We knew coming in this was going to be hot. We diluted it. It still wasn't enough. And you can see the pure saturation of the TFA and the suppression of the internal standard. The interesting thing about this, though, unlike a lot of the longer chain PFAS compounds, where if you ran something like this, you'd be seeing it in your instrument and carry over run after run, TFA does not retain to the sample metering pump, the columns, the lines. It easily purges out. So even after getting hit with a very high concentration sample like this, your next run is TFA free, and your internal standard responses are right back to where they should be. Now, handling samples of this nature in the laboratory, in physical cross-contamination, in your hoods is a different area entirely, obviously. And such samples really need to be separated and handled in isolation. But from the instrumentation standpoint, if you get an injection of a high-level sample like this, it has minimal impact, if any, on the instrument. And then so that's kind of our TFA series in a nutshell. What we're looking at moving forward to take this to the next level, soil protocol. For the most part, this is developed. TFA and short chain PFAS migrate very easily from soil into water. There isn't much difficulty there. The biggest challenge is finding a clean reference material for soils, for your blanks. Ottawa sand or other typically used reagent has significant levels of TFA in it. And finding a blank that'll be clean enough to establish what we want, as an RL is really the biggest challenge there. New internal standards are constantly coming out. They will be inserted in there, as needed. And the analyte list, I'm sure, will expand. Hopefully before the end of the year, we'll see maybe potentially an EPA offering in the 500 series, in which this method would undergo whatever necessary revisions to be compatible with that. But of particular interest is incorporating TFA and the short chain analysis into top assay results. Part of that mass balance that we know a lot of those precursor compounds end fate will end up as short chain PFAS compounds that might fall outside the traditional scope of 1633, and being able to offer this on a pre and post oxidation result, has considerable value.